Ahí estamos. Muy buenos días a todos. Soy Luciano Rossi de la Secretaría de Posgrado de la Facultad de Ciencias Exactas de la Universidad Nacional de La Plata. Hoy estamos en una nueva defensa de tesis doctoral, en este caso el licenciado Joaquín Liniado. En este caso la tesis va a estar íntegramente hecha en inglés, por lo cual les solicitamos en YouTube que pongan los subtítulos para el que lo desee. Joaquín, muchos éxitos. Te paso la palabra.
Muchas gracias. Bueno, thanks everyone for being here. Thanks to the examiners for having agreed to be the juries. And thanks, Horacio, for being my advisor for all these years. So my talk is about Chern-Simons theory and integrability. This is work that I have been doing for 4 or 5 years, and it is therefore a little bit difficult to condense all of that work in a 1-hour talk. So since I want to talk a little bit about everything I've done, the solution is to talk very superficially about everything that I have done, which is what I will do. So let me start with an informal motivation. So it has long been known that mathematics is a language which is used to best describe physics, and specifically among the mathematical objects that one can use to do physics, there is a very important one for physicists, which are differential equations. And unsurprisingly, differential equations are in general extremely difficult to solve. So given a differential equation, usually we don't know how to solve these equations. Yet, among this vast family of differential equations, there is a subset, differential equations, which are known as integrable equations, which due to some very particular structural property, they are essentially solvable. When I say essentially, it's because they can either be exactly solvable or you can get very close to solving them exactly. And notably, integrable equations appear not only in many areas of mathematics, but they also appear in many areas of physics, ranging from planetary motion, fluid dynamics, condensed matter physics, and in what we or I am interested in particular is in quantum field theory. So, quantum field theory stands perhaps as one of the most successful and at the same time most complicated theories in modern physics. And the differential equations that appear in this context are typically intractable. So the fact that we can find integrable structures within quantum field theories is truly remarkable. And in the context of quantum field theory, integrability is not necessarily always related to exact solvability of the differential equations, but instead there is they usually, in quantum integral field theories, they usually have an infinite number of conserved quantities. Whenever one has a system which has an infinite number of conserved quantities, the system becomes highly constrained, and that can get you either to the solution of the system or get you close to the solution of the system. And while physicists have long identified quantum field theories which are integrable, for many decades, there was no real understanding why these quantum field theories were actually integrable. And this was until a series of beautiful papers came out between 2017 and 2019, which were a series of 3 papers, the first written by Kevin Costello, Edward Witten, and Masahito Yamazaki, and the last one by Kevin and Masahito alone, in which they realized that they could explain the origin of some integrable field theories from a higher dimensional gauge theory, which is Chern-Simons theory. And so this thesis was, or this PhD was a deep exploration of this correspondence between Chern-Simons theories and integral field theories. So I will talk about systems which are widely recognized as integrable, and then I will also talk about some systems which may exhibit integrable structures, and I will do so for theories in several dimensions. So the outline the precise outline of the talk is based on how I decided to write the thesis. So first I will talk about integrability, and then I will try and explain how all of these different notions of integrability can be understood as originating in Chern-Simons theories. Okay, so the first notion of integrability is perhaps the most popular, and is the one that was related to the original correspondence, which was between Chern-Simons theory and two-dimensional integral field theories. So let me say what being Lax integrable means. So let's say we have some classical field theory defined on some two-dimensional manifold with coordinates t and x. And integrability in this context is related to the existence of an object which is called the Lax connection. So the Lax connection is a connection one form which is constructed in terms of the fields of the theory, and which additionally depend on some parameter which is called the spectral parameter, which is valued in the Riemann sphere. And the claim is that a theory is said to be, I use the word Lax integrable, if the equations of motion of this action are equivalent to a zero curvature equation for the connection. So if the equations of motion of the theory are equivalent to the flatness of this Lax connection, then the theory is said to be integral. And the reason is that if one has a flat Lax connection, one can construct an infinite number of conserved quantities, which was one of the properties characteristic of integrability. And the way one does this is one considers the holonomy of the Lax connection, which is the path order exponential of the connection. And crucially, if the connection is flat, then this holonomy is independent of the choice of path. So using this independence of the path, one can take the trace of this holonomy, which is what physicists know as the Wilson line, and one can show that the path independence implies that this trace is conserved in time. And here is where the appearance of the spectral parameter plays a fundamental role, because due to the dependence of this Lax connection, the spectral parameter, then everything depends on this spectral parameter, and one can do a Laurent expansion of this Wilson line. And since this object is conserved, then each of the coefficients of this expansion must be conserved, and this is how one constructs the infinite number of conserved quantities. So the typical example of a two-dimensional integrable field theory in the Lax sense is known as a principal chiral model. So the principal chiral model is this action defined on some twofold sigma, and the fundamental field is a function valued in some Lie group. And one can write down a Lax connection for this action. So note that this Lax connection is written in terms of the fields of the theory, and depends on the spectral parameter. And if one computes the curvature of this connection, one finds that the curvature is given by this expression here. So note that we have two different lambda-dependent coefficients. And so for the curvature to be zero, which was the condition for Lax integrability, both of these have to be zero independently. The first term is zero identically, it's a Moore-Cartan identity, and the second term is precisely the equations of motion. So this example shows how the equations of motion are equivalent to the flatness of the connection. Therefore, this is why this model is Lax integrable. Okay. So before I said that for many decades, physicists didn't understand where the integrable structure came from. And in particular, the precise statement is that people didn't know where the Lax connection came from. So in this slide here, I said this is the Lax connection, and for many years, people found this object via brute force. And part of the correspondence tries to address the origin of this. Actually, it addresses the origin of this correspondence. Okay. So the next form of integrability I will discuss is infinite dimensional symmetry algebras in 2 dimensions. So here I will focus in a very specific model, which is a Wessel-Witten model, which is this very famous action, which is the principal chiral model plus the Wessel-Witten term. The Wessel-Witten term is a topological term, and among the many interesting things that this action has is the fact that it is invariant under this transformation. So one can take the field, and one can perform here Z and Z bar are the coordinates of sigma, which we take to have some complex structure. And so one can perform this transformation, which is a left action by an anti-holomorphic function and a right action by a holomorphic function, and one can verify that this is a symmetry of the action. And indeed, these symmetries actually generate an infinite-dimensional symmetry algebra, which is known as the Kac-Moody algebra. Indeed, one has, as usual, corresponding to every symmetry, one has a conserved current, and the current corresponding to the right-acting holomorphic symmetry, we call it J, and J satisfies the same differential constraint than R, so therefore it is also holomorphic. And a holomorphic function in the complex plane always admits a Laurent expansion, and so these modes J sub n are the modes which are conserved. But furthermore, one can compute the Poisson brackets between these modes, and one finds the structure of the algebra. So this is the structure of the Kac-Moody algebra, which is an infinite-dimensional affine Lie algebra. But there is much more to the Wessel-Minowitten model, which is what makes it so special. One can actually go a step further and define the stress energy tensor using the currents, and one can do this at the quantum level. That's why I have the normal ordering symbol there. And one can show that this stress energy tensor is both conserved and traceless, and therefore the Wessel-Minowitten model is conformal at the quantum level. And so one not only has the full Kac-Moody symmetry, but one also has the Virasoro symmetry, and the existence of these two infinite-dimensional symmetries can be put together to strongly constrain the correlation function. And these procedures of constraining the correlation functions leads to an equation which is called the KZ equation, which is the Knisnik-Samolov equation, which is a differential equation for the correlation functions of primary fields, which in many cases can actually be solved exactly. So in this sense, the Wessel-Minowitten model is an exactly solvable quantum field theory, and solvability is the strongest condition of integrability. So one can also call this system integrable. Okay, so again, one would ask the question, where does this infinite-dimensional symmetry come from? So the next two definitions of integrability or notions of integrability are certainly not as standard as the ones that I have recently mentioned. These are a mixture of a proposal and a want-to-be definition of integrability, which of course are motivated, but everything that I'm going to say in the next two, 1.3 and 1.4, is not as standard or rigorous as what I said in the previous two. So this is the warning slide. This is a warning slide because many of the objects which will appear in the next two definitions come from something which I will talk about at the end of the talk. So everything will come in pairs, and the reason why I'm talking about this now was to first talk about integrability and then talk about Chern-Simons theory. But if there is something that feels unmotivated or where does this come from, don't worry. Hopefully, it will be clear by the end of the talk. Where does it come from? So the first, and one more thing, that these are definitions of integrability, not in two dimensions as they were before the previous two sections. This is in three dimensions. This is a proposal for integrability in three dimensions. So Lax integrability in two dimensions was defined using the Lax connection. We got the Lax connection and we considered the holonomy, and we used this holonomy to construct the infinite number of conserved quantities. And so the idea is to generalize this to three dimensions to try and construct some three-dimensional generalization of the holonomy, which would be, rather than a path order exponential, a surface order exponential. So remember that the holonomy W is actually the solution to a parallel transport equation along some path. And in particular, this relies, of course, on having some connection with which tells you how to parallel transport along paths. And so what we want to do is to generalize this to 3 dimensions. And so we want to define an object which we can use to parallel transport along surfaces rather than paths. And as I will argue, this requires introducing a higher connection, which will be constructed from higher tensorial data. And the way I'm going to do this is the way mathematicians have chosen to do it, which is to work with the space of paths. So at first sight, this might not feel the most natural thing one would do, but it turns out that it fits very naturally in the framework of higher group points, and in particular, it allows one to generalize these ideas to arbitrary dimensions. So remember, the space of paths is defined literally as the space of paths in some manifold. Here the manifold is 3-dimensional manifold Y, and so Py is the space of smooth maps from the interval to Y. And so the way we will define a surface is by considering a path in this space. So why does a path in path space define a surface? So let us consider this map, which goes from the interval to Py. Gamma will be the path. So gamma of naught, for example, is an element in Py, which is itself a path. So gamma of naught is a path. Similarly, gamma of 1 is another path. And for every t between 0 and 1, gamma of t is a path. So all together, all of these paths form together a surface. And the reason why we do this is because we can now define the surface holonomy as a path order exponential, but working on the space of paths rather than the manifold itself. So before we define the holonomy as the path order exponential of the interval over some path of a connection. Now we're going to do exactly the same, but now this path gamma will be a path on path space, so therefore a surface, and this connection has to be some connection on a bundle over this space, which is Py. And now people have constructed connections over Py, and here I will only give the expression. And to construct this connection, one uses a 1 form and a 2 form. So the 1 form is what usually one has as a connection, and this 2 form appears because now we're talking about surfaces. So the expression of the connection has this 2 form B, and it has this W. So W here is the parallel transport operator, is the holonomy of A. And so conceptually what's happening is that W tells you how to move along the borders of the surface because W knows about parallel transport on paths, and B tells you what's happening inside the surface. And B is a 2 form because in a surface you have 2 directions. In particular, all of this is to basically use this object in the same way that we did in 2 dimensions to construct an infinite number of conserved quantities. And in order to do so, we will need this connection to be flat. And one can show that for this connection to be flat, one can express the condition of this connection being flat in terms of conditions on this 1 form and this 2 form. And indeed, this connection curly A over path space will be flat as long as the curvature of the usual connection of the 1 form is B, and then the covariant derivative of B with respect to A is 0. So why do we do all this? In the end, doesn't matter if it wasn't that clear the construction. As I said, everything has to be done in a slightly superficial manner, but the essence is that we now have this object which we can understand as a surface order exponential, which is the 3-dimensional analog of the path order exponential which we constructed for the 2-dimensional case. And in particular, if this connection here is flat, even as it is defined as a path order exponential, if the connection is flat, it will be independent of the surface, and the surface independence allows us to take the trace of this object, and the trace of this object will be conserved in time in complete analogy to a 2-dimensional setting. In particular, if one had that this connection here depended on some spectral parameter, then as in the 2-dimensional case, we would be able to Laurent expand and if this object is conserved, then these coefficients will also be conserved in time. And in this way, we will be able to construct an infinite number of conserved quantities. So this brings us to the definition of higher-Lax integrability in 3 dimensions, which is basically, let's say we have some field theory of a 3-dimensional manifold Y, then we will say that integrability in this context is related to the existence of a 1 form and a 2 form, from which we can construct this curly A, this connection of the path space, and we will say that the theory is integrable if the equations of motion are equivalent to these conditions on the 1 form A and the 2 form B, which were precisely the conditions for this curly A to be flat, which was what then allowed us to construct the infinite number of conserved quantities. Okay, infinite dimensional symmetry algebras in 3 dimensions. This is something I'm currently very excited about, so I will take a bit more time on this section. So I will start with a motivation. When I talked about the Wessel-Witten model, the essence of the Wessel-Witten model was the fact that it had this infinite dimensional symmetry algebras, it had the Kac-Moody algebra, and it had the Virasoro algebra as symmetry algebras. And essentially, the existence of these 2-dimensional infinite dimensional chiral algebras is related to the fact that these models are conformal invariant, and conformal invariance in 2 dimensions, we know that this local conformal invariance is infinite dimensional, but that's something very special to 2 dimensions. So infinite dimensional symmetry for conformal symmetry only happens in 2 dimensions. If you go to d equals to 3 or higher, the local conformal group becomes equal to the global conformal group, which is finite dimensional. That's Liouville's rigidity theorem, which breaks every possibility of having the power of infinite dimensional chiral algebras for conformal field theories in dimensions higher than 2. And so what people have done for years was to try and find inside higher dimensional systems 2-dimensional chiral algebras. So there was a very famous paper by Bean, Patel, Lemos, and collaborators in which they found this 2-dimensional chiral algebra structure inside n equals 2 superconformal field theories, I think that in 6 dimensions. Then now Kevin and collaborators have been working on finding chiral algebra structures inside 4-dimensional theories in relation to celestial holography. So people look for chiral algebra structures inside higher dimensional theories in order to be able to use the power of infinite dimensional symmetry algebras. And here, what I'm going to tell you about is a proposal which instead of trying to look for a chiral algebra inside a higher dimensional theory, the idea is to generalize the notion of a chiral algebra to an object which is suited to describe 3-dimensional theories. So let me try and argue where this is coming from. So remember that in the Wessel-Witten model, the infinite dimensional symmetry could be explained by the existence of this right-acting symmetry, which had correspondingly a conserved current, which was holomorphic. So the del bar operator acting on J is equal to 0, which means that it's holomorphic. And we can understand this expression here from a cohomological perspective. So remember that the cohomology of a differential was defined by all of those guys who are close with respect to a differential, so that when I act with the differential, it gives me 0, quotient it out, but all of those guys were exact, so that they are d bar of someone. And one can show that J is not exact, it is closed, and therefore it's an element of the cohomology. And if you ask a mathematician what this cohomology looks like, they will tell you it looks like Lorentz polynomials. So this is a very fancy way of saying that J being holomorphic admits a series expansion. But the reason why I talk about this is because this can inspire us to how to generalize this story to 3 dimensions. So let's say that now we're working with a theory rather than in the complex plane. We're working on R times C. And so one can ask, is there some differential in R times C such that its cohomology looks something like Lorentz polynomials? And surprisingly, there were Nicholas Garner and Williams asked this exact question. And in a paper which came out very recently, 2023, they studied the cohomology of operators of these differentials on R times C. So in particular, they studied the cohomology of this differential, d prime, which is the derivative along tau, which is the real direction, and the del bar operator. And they show that the cohomology of this differential indeed yields a space which is analogous to that of Lorentz series. So the feeling is they are giving you something which tells you if you find a theory such that it has a symmetry, such that the symmetry satisfies that this differential acting on the symmetry or the current is equal to 0, then all of this technology allows you to write down an infinite mode expansion for this theory. But Garner and Williams in the paper, they don't have that theory. They only say if you had that theory, then you would be able to do this. And in some work we did last year, without knowing, we actually found that theory. So this is a theory which, in the end of the talk, you will understand where does it come from, but by now it is a three-dimensional theory defined precisely on R times C. So the fields of the theory are a field G and a one-form theta. Both of them can be taken to live in a Lie algebra. So G in a Lie group, but the more Cartana current in the Lie algebra. And we have it has this expression which might not look like something you have seen before. Also, we have this object, mu1, which is a map from the Lie algebra to itself, which in principle can be taken to be general. So to bring this to something that you might have seen before, if one takes, for example, mu1 equals to 0, then this term vanishes, and one gets only this term. And performing some field definition, one can show that this action, in the case in which mu1 is equal to 0, can be obtained by doing some gauge fixing of BF theory. So this action for mu1 equals to 0 is classically equivalent to BF theory. Whereas if one takes mu1 equals to the identity, for example, one finds that this action, after some field definitions, is exactly equivalent to Chern-Simons theory. So this is a three-dimensional action, which is somewhere between BF theory and Chern-Simons theory, and which, in particular, it has a symmetry, which is, well, the fields come in pairs. As I said, many fields come in pairs. The fields come in pairs, and so do the symmetry transformations. And this action has this symmetry, so one can change G via an action to the right, and theta via what looks also like an action to the right. And this transformation of the fields will be a symmetry of the theory as long as the parameters satisfy that d prime acting on, which was the differential that Garner and Williams studied, acting on the symmetry parameters is equal to 0. This implies that one has conserved currents associated to the symmetry transformations, and the currents will satisfy exactly the same condition, which is that d prime of the currents is equal to 0. So, using the technology developed by Garner and Williams, one can say, okay, so we have found an object which is d prime closed. One can show that it is not exact, and it is therefore an element of the cohomology of R times C, which is what Garner and Williams studied in their paper. And so they said, if you find something that is an element of this cohomology, this is how you write down a mode expansion. And so this allowed us to write an infinite mode expansion for the currents associated to the symmetries of this theory. And in particular, one can perform a symplectic analysis of the theory, and one can show that the modes satisfy an algebra, which looks very, very similar to the Katsunori algebra, but a generalization to one dimension higher. And well, this is something we published in a very recent paper a couple of months ago, I think, with Hank Chen. In particular, one finds here that each of these modes is a conserved quantity, and therefore, in this sense, one can understand a theory having this infinite dimensional symmetry algebra to be integrable. There is more to it. We believe that one can actually quantize this theory and perform techniques similar to those of conformal field theory, but that is something we are currently Okay, which brings us to the last definition of integrability that I will consider, which is in 4 dimensions, and it's anti-self-dual Yang-Mills theory. So anti-self-dual Yang-Mills is a subsector of self-dual of full Yang-Mills theory. So Yang-Mills theory is given by this action, which is F star F, where F is the field strength of the connection A. And the equations of motion of this action are given by the covariant derivative of the Hodge dual of F with respect to A. And in particular, these are differential equations which are very, very difficult to solve. However, inside the space of solutions to these equations, there is a subset which comes from imposing the self-duality condition. So self-duality condition or anti-self-duality condition is the statement that the F is equal to plus or minus Hodge dual, and in particular, any A such having a field strength which is self-dual or anti-self-dual will immediately be a solution of the full Yang-Mills equations, because if you replace here star F with F, then you get the Bianchi identity, which is identity 0. And notably, this subset of solutions, of course, not every solution. Full Yang-Mills equations are self-dual or anti-self-dual, but every self-dual or anti-self-dual field is a solution of the Yang-Mills equations. In particular, these anti-self-dual Yang-Mills equations are integrable. So to understand why these equations are integrable, one has to pass through twistor space, and in particular Euclidean twistor space. So Euclidean twistor space is a complex manifold, 3-dimensional complex manifold, which was introduced by Penrose in the 1960s. He was trying to unify general relativity and quantum mechanics, and he was trying to do so using complex manifolds. And explicitly, twistor space is defined as a non-trivial C2 bundle over CP1. So remember that a bundle usually has a base space and then fibers, and the triviality or non-triviality of the bundle is related to how one sticks the fibers on the base space. And the fact that twistors, so here the base space is CP1, the Riemann sphere, which I drew as a line because so the drawing was neater, and then the fibers are copies of C2. And the way in which they are stuck is non-trivial in the sense that as you move along CP1, the conflict structure in each copy of C2 changes. So what is being holomorphic or anti-holomorphic as you move along the base changes in each copy of C2. So that's twistor space. And twistor space allows us to talk about the Penrose word correspondence. So this was a correspondence brought, of course, by Penrose and Ward, which relates. So twistor space is itself a bundle, but one can use twistor space as the base for another bundle. So here we have the drawing of twistor space as the base, and these hairs to be the fibers. And the Penrose word correspondence relates holomorphic vector bundles over twistor space. So whatever that means, the important thing is that to have a holomorphic vector bundle over twistor space, one requires a connection which is partially flat. And the Penrose word correspondence identifies bijectively. There is some additional constraint, which is that the bundles have to be trivial one restricted to CP1, but it doesn't matter. They identify these connections with solutions of the anti-self-dual Yang-Mills equation. So Penrose and Ward tells you there is, for every solution of the anti-self-dual Yang-Mills equations, you have a holomorphic vector bundle of twistors. And one would wonder how can this be helpful in what universe? And surprisingly, the answer to that question is a 3-page paper by none other than Attia, Drenfeld, Hitchin, and Manning, where they find solutions, exact solutions to the anti-self-dual Yang-Mills equations precisely by constructing holomorphic vector bundles over twistors. It turns out that constructing holomorphic vector bundles over twistor space is actually easier than solving the anti-self-dual Yang-Mills equation, because it's, in the end, a purely algebraic problem. And so they construct the holomorphic vector bundles over twistor space, and they use the connection of those bundles construct the solutions to the anti-dual Yang-Mills equations. And so in this way, they find solutions to anti-dual Yang-Mills equations, which they call instant dots. And in particular, given that these equations are differential equations, which are solvable, they are, of course, it. Okay, so let me close with a summary with all of the conditions that I have spoken about integrability. So Lax integrability in 2 dimensions was related to the existence of a flat Lax connection. Then the infinite dimensional symmetry algebras were related to the existence of these symmetries, which allowed an infinite dimensional symmetry structure. Then higher or 2 Lax integrability in 3 dimensions was related to the existence of this flat connection over path space, which in turn was written in terms of this 1 form and this 2 form B, that for the connection over path space to be flat, one required these conditions on A and B. Then I talked about infinite dimensional symmetry algebras in 3 dimensions, which was related to this generalization of a chiral algebra to 3D, which was related also to the existence of these symmetries acting on these fields. And finally, I talked about anti-dual Yang-Mills, which was related to the existence of holomorphic vector bundles over twistor space, which were characterized by this equation. So if we look at this slide, we see that integrability can be strongly related to flatness of a connection and infinite dimensional symmetry algebras. Which brings us to the second part of the talk, which is Chern-Simons theory. So Chern-Simons theory is a gauge theory defined on a 3-dimensional manifold. Chern-Simons theory is very famous for many reasons, but what is most important for us is that the equations of motion of Chern-Simons theory are precisely flatness for the gauge field. So one looks at this and one says, oh, this has to certainly be related to integrability, because we have seen that flatness appears in integrability non-stop. One has an action whose equations of motion are flatness, then there should be some relation. But this Chern-Simons theory was known by many people for many years, particularly by Witten. Witten knew that, suspected that there had to be a relation, but he writes in a note that he didn't know how to actually do it. And so remember he writes in a note that he didn't know how to do it. So let me try and argue why one can't do it as it is. So remember that the original correspondence between Chern-Simons theory was related to Chern-Simons theory integrability was related to 2D Lax integrability. So Chern-Simons theory has equations of motion which are equivalent to a flatness of a connection. So why doesn't it work? Why couldn't Witten make it work? So first thing that one has is one writes this connection and one says, but my Lax connection, I wanted to have only 2 legs. And this one has 3 because I'm in a 3-dimensional manifold. But then you can say, but you can use the gauge symmetry of the theory as usual to kill one of the components of this connection. So now you have 2 components. But then the problem is that remember, we require this as a spectral parameter. The spectral parameter was crucial to be able to mode expand in an infinite series. And here, x1, which is the remaining coordinate, is real. It's not complex. So one can say, well, let's then complexify x1. But if you complexify x1, then you will be working on a 4-dimensional manifold, and now your gauge field will have 4 legs, and you can only kill one using the gauge symmetry. Turns out that actually complexifying x1 is the right thing to do, but you have to do it very, very carefully. Which brings us to 4D Chern-Simons theory. So to write down 4D Chern-Simons theory, this was the great insight by Kevin, complexifying this coordinate and writing down this action, which one complexifies one of the real directions to simply 1, and so on. Now one has this 4-dimensional manifold, simply 1 times R2. Chern-Simons is a 3-form, so if one wants to write down an integral over a 4-dimensional manifold, one has to put a 1 form here. And this choice of 1 form is what makes the trick. So dz is a coordinate on simply 1, and so note that here having dz here makes that every z component appearing from this expression here will automatically die when wedged with this dz. So now our gauge field, we will only care about 3 of the components. But note that this one form has poles, and the poles of this one form are absolutely essential. So this one form has a pole at 0 and a pole at infinity. Both of them are simple. And one can think of the poles live on CP1, and one can think of the poles as being little holes, CP1, and whenever you have a manifold and you make a little hole, what you're doing is fabricating a boundary on that manifold. And whenever you have a gauge theory and you put a boundary in the gauge theory, usually the boundary breaks the gauge symmetry. And so this breaking of the gauge symmetry induces dynamics precisely where the symmetry is broken, which is at one copy of R2 at each of the poles. So indeed, for example, one can understand this by saying, okay, I want to fix AZ bar, this component, to 0, so I get something that looks like a lax connection. And one realizes that one can do that everywhere where one has gauge symmetry, except for the location of the poles where the gauge symmetry is broken. So if one insists in fixing AZ bar to 0, then this is what naturally induces dynamics. So schematically, what's happening is that one starts with the theory, 4D Chern-Simons theory here, which is on CP1 times many copies of R2. And then the poles, what they do is they induce dynamics on copies of R2. Crucially, the connection, which one starts here, after gauge fixing Z bar to 0, becomes a 2-component connection, which is a lax connection. This is extremely schematic. And in particular, the dynamics induced here are inherited from the dynamics of the parent theory, which are flatness of the connection, because the equations of motion for the Chern-Simons theory, they are also flatness. And so this is what allows one to construct two-dimensional integral field theories with lax connection in a systematic manner, and this somehow gives an explanation to the origin of the lax connection. One can think that the lax connection is actually coming from a higher dimensional gauge theory, which is for the Chern-Simons theory. In particular, the choice I wrote down before, which was dz over z, one can choose many different one forms, and the different choices of one forms lead to different two-dimensional integral field theories. In particular, if one chooses dz over z, one gets the Wassermann-Witten model. And if one chooses, for example, z squared minus 1 over z squared, one gets the Prince-Vickers model. So many two-dimensional integral field theories have been constructed in this framework since these papers came out. It's not known if all of them. And in particular, this is where I did like the first thing I did in this context was in relation to this correspondence. This was in collaboration with Benoit Vicedo, where we considered a very general one form, and we showed that for that very general one form, one finds a big family of integrable models, which are known as degenerate T models. Now I'm going to swap the order, and I'm going to first talk about 6D Chern-Simons theory on twistor space, so which will be related to anti-Septuagint and Mills. So in 1995, Witten was studying the topological B-string, and he introduces this holomorphic Chern-Simons action for the open string theory of the string. And this action is defined over a three-dimensional complex manifold. So this A is a 0-1 form. So this is a 0-3 form. So for all of this to make sense, this has to be a 3,0 form. And this is why one requires that the manifold X is Calabi-Yau, because the definition of being Calabi-Yau is that it admits a globally defined nowhere vanishing holomorphic 3,0 form, which is precisely what one wants to write there. In particular, the equations of motion of this action are this partial flatness, which, if we remember, this was precisely the condition for a holomorphic vector bundle over twistor space to be holomorphic. In particular, we know that twistor space is a three-dimensional complex manifold. We know that this action has equations of motion which define the corresponding vector bundles. It would be beautiful if we could simply put X where we have X twistor space. The problem is that twistor space is not Calabi-Yau, so twistor space does not admit a globally defined, nowhere vanishing holomorphic 3,0 form. And again, Kevin suggested a solution to this problem. He realized that yes, twistor space is not Calabi-Yau, and it does not admit a holomorphic, nowhere vanishing, globally defined 3,0 form, but you can put a meromorphic. You can put poles to the object. You can put poles to a 3,0 form, poles, then you are completely free to do it. And so one writes this action where one has this 3,0 form, which now has poles. So here we have the coordinates zeta, which is the coordinate on CP1. Remember, twistor space was a non-trivial bundle of CP1 with fibers C2. So locally it is CP1 times C2. And the coordinates are zeta, the coordinate of CP1, and B1 and B2, the coordinates of the holomorphic coordinates of C2. And essentially, now if one looks strong to this action, one realizes that this looks something very, very similar to the 4D Chern-Simons action. Because one has a Chern-Simons 3 form, and then one has an object which has poles. And furthermore, twistor space as a real manifold is exactly equal to CP1 times R4. So real manifolds don't care about complex structures, and the non-triviality of the bundle of twistor space was related to the complex structures. So if you don't have complex structures, twistor space doesn't care. And so as a real manifold, it is CP1 times R4. And so if one looks at this strongly, one feels this looks very similar to 4D Chern-Simons theory. And indeed, one can do the exact same thing that one does in 4D Chern-Simons theory. One can start with this 6-dimensional theory, and one can perform some magic, and one gets an induced theory on R4, and notably the connection on 6D becomes a connection on R4, and the flatness of the connection of the parent dimensional theory becomes the anti-Sertoli Mills equations on R4, which gives an explicit realization of the Penrose-Ward correspondence through an action principle. But there is more to it. So what I have just shown is going from 6D Chern-Simons to anti-Sertoli Mills on R4. But starting here, one could ask, okay, what happens if instead of killing the CP1, I perform a dimensional reduction of this copy of R4? That should eventually take me to 4D Chern-Simons, because now it will be defined on CP1 times R2. And that is something that was done by David Skinner and Roland Bittelstone. They showed that one can actually start here and go to R4 and find anti-Sertoli Mills, or start here and go to 4D Chern-Simons theory. And from each of these, one can get a two-dimensional integrability theory, and all of this diamond, each side you choose to travel of the diamond takes you to the same two-dimensional integrability theory. So this was the second thing I worked on in my PhD. So this was together with the British collaboration, was with Lewis Cole, Ryan Callinan, Ben Hoare, and Dan Thompson. So what we did was to construct the diamond for a specific choice of three form. And in particular, we constructed here integrable deformations of a four-dimensional model, which is the Western-Winnow-Witten model. So this was the first paper we wrote in this context, and then we did one more diamond, which was to construct the diamond corresponding to gauge four-dimensional Western-Winnow-Witten models. And this brings us to the last part, which is 5D2 Chern-Simons theory. So this is I'd say that the work I'm most proud of, because it wasn't the continuation of something that was done before, rather it was something we came up with. So this was done together with Hank. Hank was a PhD at PI when we did this. Now he's doing his postdoc in China, in Defensa. He's a category theorist. And so we talked, and he brought up this thing, which is a proposal known as the categorical ladder equals dimensional ladder proposal, which is a proposal from the 90s, which says that one can study higher dimensional physics by using higher categorical structures, so higher mathematical orders, whatever that is. And so, before, when I talked about two-lax integrability, which was related to this higher flatness of the curly A, which was expressed in terms of this A and B, and then when I talked about infinite dimensional symmetry algebras, which was related to these fields which came in pairs and the symmetry transformations, which also came in pairs, secretly, all of that was coming from actually working on what's known as two-gauge theory. So two-gauge theory is this higher categorical generalization of gauge theory. And essentially what one does is one replaces the fundamental mathematical structure, which is a Lie algebra, by something that's known as a two-Lie algebra. So for those who are familiar with L-infinity algebras, a two-Lie algebra is a strict two-term L-infinity algebra. For those who aren't, a Lie algebra is simply a pair of algebras, which can be the same or can be different. Here I wrote them different. And a map between H and G. So this map is actually differential, but doesn't matter. And a pairing between G and H, which can be thought as a bracket between G and H, which is G. So if one replaces the Lie algebra with a Lie2 algebra, then one is made to replace every object by a pair of objects. This is why the connection is replaced by a two connection. So A is now replaced by A and B. So A is a one form and B is a two form. And then the gauge transformations are replaced by two gauge transformations. So the usual infinitesimal gauge transformations is replaced by a pair of gauge transformations. And in particular, mathematicians, I'd say, or mathematical physicists, said, okay, let us look for an action such that the equations of motion of the action are flatness of a one connection, a two connection, a three connection, whatever n connection you are considering. So for a Lie algebra, the connection is the usual connection, a one form, and so an action whose equations of motion or flatness of the action is Chern-Simons theory. So Chern-Simons theory, these theories are known as homotopy Moore-Cartan theories. They are characterized by flatness of n connections. So for a Lie algebra, the homotopy Moore-Cartan theory is Chern-Simons theory. But for a Lie2 algebra, where one has a two connection, one has also a homotopy Moore-Cartan theory, which is an action such that its equations of motion are this condition of higher flatness, which I wrote before. So our idea was, okay, Costello and Yamasaki started with 3D Chern-Simons theory because they wanted the flatness of the connection, but they, to get it and make everything work, they complexified and compactified to go to 4D Chern-Simons theory. They put poles in the one form, and this allowed them to construct two-dimensional integral theories. And so what we did was to categorify the story. So instead, we said, okay, let's start with 4D Chern-Simons theory. Let's complexify one of the directions. This will bring us to a five-dimensional object, and then a five-dimensional theory, and then we will be able to construct three-dimensional integral field theories. So this is exactly what we did. We got the two Chern-Simons action, and we wedged it with dz over z. And following the same story that worked for 4D Chern-Simons theory, for 6D Chern-Simons theory of twistor space, putting poles here induces dynamics on this three-dimensional manifold here. And in particular, the dynamics of this three-dimensional theory are inherited from the parent theory, whose equations of motion were precisely this higher flatness. So this was the work we did, published last year. On purpose, we called higher gauge theory integrability, where we introduced this idea. So notably, this is something, of course, very new because it was done last year. And at the same time, so a couple of days before we actually published this paper, Benoit and Alexander Schenkel, a collaborator of his, published the exact same idea. But thankfully, they made a different choice of omega. And that was crucial because the choice we made leads to one of the notions of integrability I have spoken about, and the choice they made leads to the other one. And in particular, the choice we made leads to what I believe is the most fun version of integrability, but that's probably because I did it, which is what I talked about when I said, when I talked about three-dimensional theories with infinite dimensional symmetry algebras. So this is the action I wrote down before, which is a three-dimensional action we got from this 5D to Chern-Simons story, which we then studied using all of the technology of the Ravioli technology of Gardner and Williams. So this is a paper we sent to the archive a month ago, I think. Okay, so this brings me to the end. So hopefully, I know I rushed and I know I went through many things very, very superficially, but hopefully you are convinced that this thesis was a deep exploration of Chern-Simons theory and its relation to integrability. So there are many, many open avenues to continue, some of them which I am currently working, some of them which I would like to work in the future. So the first is exploring this three-dimensional theory. I strongly believe that many CFT methods will be, one will be able to apply CFT methods to this three-dimensional theory, which may eventually, hopefully, lead to some sort of exact solvability. Then, from a different angle, there is a group at PI which, Kevin and collaborators with Atu Sharma and Natalie Paquette and other collaborators are Roland, which they studied the diamond of Chern-Simons theory coupled to gravity. So remember that the holomorphic Chern-Simons theory was the open string sector, but one can couple it to a closed string sector, which is gravity. And with this, they found an example of a top-down example of celestial holography. And that's not what we're doing. Instead, what we're trying to do is trying to understand if this coupling to gravity can lead, after following the whole diamond, to some sort of TT bar deformation. It's known that TT bar deformations are related to gravity. We are exploring whether this can be done from this context. I'm doing that with Lewis, and then with Maxi here, he came up with the idea of trying to construct the 2D sigma model corresponding to the superstring on ADS4 across CP3. So this has been done for the string on ADS5 across S5. And so we wonder if we can do the same starting from 4D Chern-Simons for this. Then some things which I am not doing at the moment, but which I will be very interested in doing, is to study the relation between this 5D holomorphic 2 Chern-Simons theory and 5D Chern-Simons theory in mini twistor space. So mini twistor space is a one-dimensional reduction of twistor space, which is a 5-dimensional space, where one can also define Chern-Simons theory, and then eventually continue up the categorical ladder to define 6D Chern-Simons theory in relation to 4D IFTs. And that's all. Thank you very much.
Thank you very much. That was great.
Okay, thank you. So we're going to start with the question from the jury. Kevin, you want to start?
Okay. Thanks, Joaquín. That was a really lovely talk. You've done amazing things in your thesis. I'm very impressed. I have a couple of questions about the 3D model you constructed, which has this infinite symmetry. What does it become when you reduce it to 2 dimensions along a circle?
When you reduce it for doing some dimensional reduction, like on R, killing R, for example.
Yeah, we say you perform a symmetry reduction to turn it into a 2-dimensional model. What does
I don't know. I don't know. We haven't done it, but it sounds like a straightforward and an interesting thing to try.
I see. So it's not. There's no obvious answer.
So we haven't done it. Let me think. I don't know if I'll be able to come up with a fast answer to. I don't know. I don't know. I'll try it. I'll try it.
Okay, because it would be interesting to connect this model with the WZW model and see how the enhanced symmetry you have relates to the known enhanced symmetry of WZW.
I agree. I agree. So why did you say a circle?
Yeah, I meant we can dimensionally reduce it by placing it on, say, R2 times S1 and making the circle small. Or equivalently, you can perform a symmetry reduction. At the classical level, these are the same operation.
I see.
Let's see. For this model, I think it would be interesting. Have you ever looked at the literature on fractons and subsystem symmetries in three-dimensional field theories? That is something people like in the condensed matter literature, where they study models which have operators which are not topological, but they're conserved in some directions, but not others.
What's the name? No, I haven't looked at it. Fractons and
subsystem symmetry.
Okay. Which are condensed matter systems in 3D?
Not special to 3 dimensions, but that they study them in various dimensions. Seiberg has written papers about this.
Okay. No, I didn't know. I hadn't heard about fractals before. I'm also going to look at it.
Okay. So another question. It's more of do you know what the Hilbert space of this system looks like? Say on a two-sphere?
So, well, so one can actually do some. So one can radially quantize this theory, replacing the circle with a sphere, and one can compute OPEs and the OPEs, and then one can obtain the commutators, and one verifies that the commutators are the same. And so the next step would be to actually construct the representation theory of this thing, which is the next step of the story. I'm not sure if so. Garner and Williams, they talk about vacuum modules in their paper, and it's so what we managed to show, it's not written in the paper that's published because I have to I'm rewriting it at the moment. But what we managed to show was that one can actually show that the symmetry algebra defines a Raviolo vertex algebra, which is this notion that Garner and Williams introduced, where one has a state operator correspondence. So we managed to show there is also a reconstruction theorem in the case of Raviolo, of the Raviolo vertex, where one can show that if one satisfies certain properties, then you have all of the axioms. And well, the next step is to study the vacuum module of this theory, which is the Hilbert space.
But I would so their story is what you find if you have a theory defined which is partially topological and partially holomorphic. But your theory is better because it's not topological in any way, as far as I can tell. So would you not find both the Raviolo vertex algebra and its complex conjugate? Is that what you find? Just like the WZW model, it has a chiral subalgebra, an anti-chiral subalgebra.
I see. It's so I think no. So perhaps the answer is yes, and I'm saying no because of my ignorance. But what one finds is one also finds the analogous left-acting symmetry, as in the same way than in the Wessel-Minowitz model. But the left-acting symmetry, instead of satisfying that this D prime acting on it is equal to 0, what it satisfies is that del acting on it is equal to 0. So the only and I think that in R times C, I think, but again, this might be part of my ignorance, that doesn't allow you to write down a mode expansion there. So you find this chiral symmetry, this conjugate symmetry. Perhaps it also has some complex conjugate symmetry, which we haven't looked at and which is there, but we don't know. But for example, because the way we actually discovered these symmetries was because basically we traced them as they descended from the five-dimensional theory. So that's why we knew where to look, and we found the right-acting and the left-acting symmetry. And crucially, the right-acting symmetry satisfies that d prime of the symmetry is 0, but the left-acting symmetry satisfies that del is equal to 0. And to my understanding, which I insist might be wrong, that doesn't allow you in R times C to construct a conjugate 3D chiral algebra. But it will definitely be worth looking at, for example, some complex conjugate. Perhaps you also have a complex conjugate symmetry, which is a different one.
Okay, so I kind of imagine that this, the WZW model can be viewed as being built from a chiral CFT, an anti-chiral CFT, glued together by topological degrees of freedom. I kind of imagine something similar would be happening here, but you're saying that's not quite true.
I'm not sure. So at least not from the construction one understands from the higher dimensional gauge theory, but perhaps it is.
Okay. So another question about moving on to your work on six-dimensional Chern-Simons theory. So you guys, your story, you study a meromorphic form which has first-order poles. Am I correct in thinking, so of course, when you have a first-order pole, you need to have some kind of boundary condition for the gauge field.
Yeah.
So am I correct in thinking that your boundary condition preserves the G symmetry? Like I don't choose some subalgebra of my Lie algebra. Is that correct?
So you're talking in 6D Chern-Simons on twistor space?
Yes.
And so, yes, and it's, okay, sorry. Yeah, integral deformations. Yes, we have simple poles. And the question is, if the boundary condition preserves, yes, it does preserve some of the G symmetry, and you can trace that down.
Does it preserve all of the G symmetry, or is?
It's a good question. I don't think so. I remember. I think surely some of it is preserved because we did this computation, and I don't remember if the boundary conditions at the poles. So I would, if the honest answer is I don't remember. If I had to risk, I would say that it doesn't preserve all of it because of what happens also in 4D. But I remember.
In 4D, it does preserve. When I have a first order pole, you can just, like with the WZW model, you have dz mod z, and at each first order pole, you preserve all of the G symmetry, which is why you find.
But you mean like global or this G symmetry satisfying some further condition?
No, I just mean something very simple. You have some condition that some components of your gauge field vanish. Right?
Yes.
So it could be. So you have to. So the components of your gauge field which vanish, say, in 4 dimensions, what you do is you say AW bar vanishes for all Lie algebra indices.
Yeah.
You could also say both AW and AW bar vanish, but only for half of the Lie algebra indices. That would be something else you could do.
Mhm.
So I don't, in your 60 story, which kind of thing do you do?
Okay, I see. So in the 60 story, we in the interval deformations, the boundary condition we took was that at the simple poles, so it has a double pole at infinity and simple poles. At the double pole at infinity, we kill the gauge field, and at the simple poles, we ask for the components to be the same. That the component of we choose diagonal boundary conditions.
Oh, I see. So it's a non-local
Yeah.
condition.
Yeah, which and yes. So the reason I don't remember it is because it was kind of a while ago.
I know.
And but it's yes, it's important because that okay, I'm remembering now. That has a crucial difference between the four-dimensional Chern-Simons case, because in 4D Chern-Simons you can also have double poles and a double pole and two simple poles, and you can put diagonal boundary conditions, and that leads to a lambda deformation of the principal current model. And in particular, you have enough gauge symmetry in that case of boundary condition in order to kill one of the fields in one of the copies. Whereas in twistor space, that's not further true. You don't have enough gauge symmetry in order to kill, and this was something that drove us crazy because we didn't understand what was going wrong. Why couldn't we kill one of the fields? And the answer was you simply can't, and you shouldn't. You shouldn't. We realized that actually we needed both fields in order to be able to satisfy Andy-Dual and Mills equations. With one field, it wasn't enough. So yes, that was a boundary condition, and the gauge symmetry we had there was less than what we had, what one has in 4D.
Okay, thank you. That's clarified. I was a bit worried because if what you did in twistor space was simply to say AZ bar is 0 or something like that, then you run into the problem that that's not an elliptic boundary condition, so there's not a good propagator.
I see. Yeah.
But if what you're saying is instead, I'm kind of gluing these 2 points together where there's a first order pole, that's a good thing to do. So I'm much happier with that.
Okay.
So another question in this vein, it looks like your story with the degenerate E-models, is that how you say it?
Yeah.
This is a beautiful story where you take a Lagrangian subalgebra of, G adjoin Z modulo Z to the N. It looks like that this would also work in the 6D context. Have you considered that?
Yes, we did, and in particular, everything becomes a little bit more difficult in the 6D context because of the same reason of why it becomes more difficult in the simpler case of the two simple poles, which is that when you write down this in the 4D story, when you choose this Lagrangian subalgebra, which is one way to choose boundary conditions, it is very clear what is the symmetry, the residual symmetry with the choice of Lagrangian subalgebra, which you can then use to kill fields conveniently. And what happens is that in 6D, that relation doesn't hold as nicely anymore. We realized that when doing the 6D story, that you can take boundary conditions which don't define Lagrangian subalgebras, but still are good boundary conditions. When one of the realizations of the work of the integral deformations on twistor space was, not everything can be immediately generalized from 4D to 6D. Namely, this broad definition of taking boundary conditions defined through a Lagrangian subalgebra cannot be done immediately. Perhaps it can be done in an adapted manner and might work, and this, of course, would lead to a significantly broader family of integrable deformations of the 4D WCW.
Mm-hmm. Okay. So I don't want to take up too much time, but I do have one more quick comment that I think looking at the TT bar deformation is a very interesting direction.
Mm-hmm.
There's a paper of Victor P, which was his master's thesis at Perimeter, more or less, where
he looks 4D Chern-Simons with TT bar.
Yes, it sort of works. You find TT bar, but only on some curved geometries and so on. I just wanted to. That might be I wasn't sure if you were aware of that, and that might be a start.
Yeah, I found it the other day. Yes, thanks.
Mm-hmm. Okay, so I think that's all. That's all, and congratulations. This is some very, very impressive thesis.
Okay, thank you very much.
Okay, so I guess it's my turn. So yeah, I'll just echo Kevin that yeah, it's great thesis, great work, and a very nice, clear presentation as well. So if you'll allow me, I have some kind of like super naive, vague questions reflecting my high levels of ignorance about lots of this stuff. This kind of machine of using 4D Chern-Simons or holomorphic Chern-Simons up in twistor space and then doing dimensional or symmetry reductions, to what extent should I think of this as kind of mined out at this point? Like like these E models you and Benoit studied, the differentials have very general structure. You allow for lots of different zeros, lots of different poles. Is it conceivable that one could find a new 2D integrable field theory with this machinery nowadays, or should I view this as kind of mined out at this point?
I hadn't heard the word mined out. Let me try and
oh, okay. There's nothing left in the mine.
Yeah. Let me try and let's see. Okay, let's see if this works. But for some reason it doesn't work anymore. Okay, so I'd say that's one of the most important questions of 4D Chern-Simons theory, which is whether it actually provides a complete classification of two-dimensional integral field theories, classically at least. And to my understanding, the answer is we don't know. So, for example, when I did this work with Benoit, I thought we were considering the most general possible choice of one form, because we were putting arbitrary number of poles and arbitrary number of zeros. The truth is, it wasn't as general as it could be, because we're taking simple zeros, and because nobody knows what to do when you have double zeros or higher order zeros. And I believe that so people continue, you still see people work on 4D Chern-Simons theory and come up with different. So, for example, one thing we thought when we did 4D Chern-Simons theory was this paper with Benoit was this, what I said to Kevin before, which is that you could only choose boundary conditions defined via Lagrangian subalgebras, but then we realized doing this paper on twistor space that you could actually define boundary conditions we didn't define Lagrangian subalgebras, so that was something that if you put in our paper, that would immediately generalize it. And well, classification problems in physics are very, very important in general, and it's an open question whether every 2D integral field theory can be constructed or not. I believe that the most known and important ones have already been constructed, but there was, for example, another paper by Lewis that he also considered different reductions of twistor space. So instead of reducing like R2, he considered like reductions like via circle. And then they realized that they could actually make the spectral parameter to depend also on the space-time coordinates, and that led to new integrable models. So I don't know, people continue to work and continue to find out new things that can be done in this context, and so I don't know if one is able to construct every 2D integral field theory from this. Certainly, this has given not only a deep understanding of why do we have integrability in 2D, but also the possibility to construct many new ones. Hopefully, someday we'll know if all of them can be obtained.
Okay, thanks. I have a couple of, again, naive questions about your kind of higher notion of integrability. So you constructed this 3D model which is integrable in your sense of lax to connection, whatever. But are there known 3D models which were known before you guys and Benoit and Alex came along?
Okay, so
that one can a posteriori see are integrable with respect to the step.
So I this was a mixture of on purpose and I didn't have time. So our model, one thing of the 3D model we constructed, which is with the choice dz over z. So to construct the model we constructed, we chose dz over z. A crucial thing of dz over z is that it doesn't have any zeros. It has poles, but it doesn't have zeros. And the zeros are essential to input the spectral parameter dependence on either the lax or the 2-lax connection. So given that we didn't have any zeros, we couldn't construct a spectral parameter dependent lax. This is why we thought that our model actually sucked, because we couldn't write down a spectral parameter dependent 2-lax. And so all of the argument of 2-lax integrability, if someone asked the question you have just asked, was like, well, actually, this I don't know how we could use it, not with our model. Thankfully, then we found part of this Raviolo story algebra, which in my mind made it much more tractable and nice. However, in the paper written by Benoit and Alexander, they do consider, sorry, I'm changing like this, yes. They do consider one form with zeros. You have 4 zeros there. And so they do construct a spectral parameter dependent 2-lax connection. But the model, the 3-dimensional model they write down is not something that it's known unless you start setting things to 0 and you recover eventually that the equations of motion are very similar to the equations of motion of the Ward model, which is the 3-dimensional generalization of the PCM, which is in 2+1. So it's not that you get the Ward model immediately. That would be extremely neat and beautiful, and in particular, it would allow one to, because all of this story of 2-lax integrability, to be very, very honest, is very formal. It's not that one can get this connection and start constructing and solving quantum theories. That's the truth. And in our model, we don't even have that lax connection, and in Benoit's model, they haven't done it, at least. And I feel, given that this connection is defined as using the holonomy, the 2 form, is something a little bit more complicated, at least to first sight, than the usual holonomy. So I believe it's something that well, part of the community is working. For example, I know I think that Benoit perhaps is, I don't know if Benoit himself, but well, Ryan, I think, is going to do a postdoc with Benoit, and one of the projects he has in mind is trying to be able to match some of these 3D theories and be able to use this higher lax connection in order to be able to say something concrete.
And again, just a really dumb question. So if I think of the kind of dumbest example of a 3D integrable system I can think of, I would just say like the Bogomolny monopole equation, which is of course just a symmetry reduction of the anti-self-dual Yang-Mills equations. And is that like, is it 2 lax integrable in like a completely trivial sense that B is just 0 or something?
Well, I'd say that this is related to my interest of trying to understand the relation between 5D Chern-Simons theory and 5D Chern-Simons theory on mini-twistor space. Because in the same way that you can get anti-self-dual Yang-Mills from twistor space, you can get the Bogomolny equation monopole from 5D Chern-Simons theory on mini-twistor space. And this is one thing I'm very interested in understanding if there is a relation or not between 5D Chern-Simons theory on mini-twistor space and this 5D Chern-Simons theory on not mini-twistor space.
Yeah. Okay.
But at the same time, perhaps looking at the monopole and trying to brute force out a 2 lax connection, which might be, as you say, trivial or easy, could be also an option to try and address this problem from different angles. Like, okay, if I have the 2 lax connection, well, that would be a very strong statement.
Yeah. Okay. Cool. And also like a little bit related to this. So in this kind of in this kind of story, I mean, in the kind of 60-40 2D story, there was this diamond, right? And then for 3D, you now kind of have one line, I guess, whatever the bottom left line of the diamond. Do you expect there to be something like a Ward correspondence for 5D integrable systems?
So a Ward correspondence. So I thought you were going to ask, do you expect that you can do something like this, which was related to perhaps Kevin's question that he asked, what happens if you reduce your 3D model to 1 dimension lower? Which I think would be...
No. I mean, is there some kind of like, a super naive thing? Well, actually, no, I don't know what to say. Actually, I was going to say something stupid. So I don't know what to say. But something like a twister construction in 7D.
I don't know.
Well, yeah, neither do I. But it would be interesting if there was actually a diamond, here as well.
But like twisters in 7D. This is the paper by. This is related to a paper by Lionel and Atul. That was on 7D.
Yeah. So they have this story about certain chiral, a construction of certain chiral higher spin theories using a kind of S1 bundle over twistor space.
Okay. Well, no, I don't know. I don't know if it would be lovely.
With your story is anyone's guess, I guess. But it would be interesting.
No, sorry. What I was saying before related to Kevin's question was perhaps you could write a diamond in which you where you have doing dimensional reduction from the 3-dimensional theory, and so Kevin asked, what happens if you dimensionally reduce your 3-dimensional theory? Do you get Wasumino-Whitman? So you could ask that same question at the level of 5D, 5D Chern-Simons. What happens if you dimensionally reduce 5D Chern-Simons? Do you get 4D Chern-Simons? That would be the analogy of the diamond. And that's also a very good question. And it would be lovely if all of that actually works.
Okay. And then let me. This is something I always like to try and do. Let me put my bad cop hat on, and suppose I was just completely unsympathetic to this area of research entirely, which of course I'm not. To an outsider, how would you what would you say is like the kind of what do you see as the kind of long-term utility of this approach? Is it in classifying integrable systems, Or are there certain computations one hopes to be able to perform in integrable systems that you think this kind of machinery can help with?
So it's fun because the naive questions are the most complicated one usually. So, so when I started working on this, I didn't have the slightest idea of what could actually one do with this. Then as I started to understand a bit more what this was about, I said, oh, let's classify all 2D integral field theories. Then I started working on twistor space, and I was like, oh, twistor space, what an interesting thing. And now I constructed this three-dimensional theory, and I say, this is the future. And so I feel that the beauty of this correspondence is not so much, it's like constantly appearing, you know, the more I explore, the more unexpected things appear. And sometimes I feel like, well, I feel that I'm tired of working with this correspondence, and then something very interesting comes up. So if in the integrability community, people were expecting the fourth paper of gauge theory and integrability 3, which intended to address the quantization of two-dimensional integral field theories. And so that was one of the possibilities, trying to understand. So in 2D integral field theories, there is this big problem, which is non-neutral locality of some theories, which do not allow one to do the quantum inverse scattering method, which leads to the quantization. So one of the possibilities is that 4D Chern-Simons takes you to that. But then, I don't know, like my feeling is that this touches many different areas of mathematics, and there are like very incredible relations which are highly non-trivial, and so I feel that the expectation is more than the expectation. I came to the conclusion that it's rich. It's clearly rich. It's a very rich structure, and the more I look at it, the more things will pop up. It's difficult to say what is the ultimate goal. I don't know. I found this 3D theory, and I'm very excited, and perhaps this leads to something very interesting, and perhaps it does. Perhaps I don't know. I feel that. Trying putting, very, very high-end goals sometimes, doesn't allow you to see the real beauty of the thing, which is itself, not necessarily where you go in solving quantum gravity, or, I don't know.
No, that's a good answer. So, okay, I think that's probably enough questions for me. Thanks very much, Joaquín.
Okay, thank you.
Okay, I think it's my turn now. Well, I'm impressed, Joaquín. It's I enjoy a lot reading the thesis. So it's a pretty good example that, sometimes if people get the idea that integrability is something that just takes place in two-dimensional, it's a very good example that there is many more things interesting related to integrability than just physics in two-dimensional. So my questions are few and quite naive, I guess. So you seem to consider always that the spectral parameter belongs to CP1. Why is that? You can consider.
So you don't have to consider always the spectral parameter to be valued in CP1. You can actually consider higher genus surfaces, so Riemann surfaces with more holes. And this is something that people have worked with. So Sylvain Lacroix and Anders Wahlberg have actually addressed that question, and they did it for.
The formalism becomes more complicated. The analysis of poles and zeros.
Well, yes, you have to change, and the boundary conditions become different, and so that's something. This is a good question. A good question to answer same question, which was how can you generalize this? Well, one way to generalize this story, which leads to further two-dimensional integral field theories, is precisely changing the Riemann surface, and that leads to different kind of models, which are, I think, elliptic. They're called elliptic models, and well, also that question also is valid for something similar at the twistor space level. Because in twistor space, you also have a copy of CP1. But twistor space is quite a closed structure, and I think I don't know if they have followed through, but at some point a student of Kevin's was, I think, working with this. But yes, it's a completely new thing that you can do, and certainly interesting.
Right. So in this correspondence between the CP4 Chern-Simons and this integral theories in dimension here, at some point you use equations of motion. So this correspondence is in principle at the classical level.
Yes.
Only. So what are the chances to explore the correspondence, the quantum level, or the integrability of those models? This combines.
So that's a great question, and I think that my answer will not be entirely correct, and it's because at some point you actually do go on shell. So one would say, well, then you are already now everything I say from now on it's valid classically. And this is because this is the way I learned to do it, but I'm not sure if this is the way. The only way that it can be done. For example, there is. So the honest answer is I'm not sure. But for example, I know that in a paper in a quite a recent paper that they work on this thing on this part here, which is essentially analogous, because also when going from here to here, if you follow the same procedure, you also go partially on shell. If you want to do this, but you couple this theory to gravity, this is something that Kevin did in a paper. He didn't go to the four-dimensional theory by going on shell, rather by computing some propagators. I'm not sure if to what loop level, if it wasn't something more than 3 level, and then finding an action like perturbatively that matches it. So I suspect that you can do something similar, but that isn't the way I learned it. That's the truth, and so I'm not sure.
There was a section or a chapter in the thesis where you consider some Archie flows. So those were corrections in the CP, the four-dimensional Chern-Simons, were those.
Okay, so that was in.
She can't read it.
No, I say because I think that was. The RG flows were perhaps in the.
Spectrum. Yeah, 561.
Let's see. 5. Five, 6. ¿En castellano o en inglés?
No, en inglés.
So, equation 561?
No, sección. La 133. H.
Okay. Here, the RG flows. Okay, so, sorry, let me remind, because this was also in bit of an old paper, well, old couple of years. So I think the RG flow was we were analyzing the flow of the. You have in the one form some parameters.
Well,
See, you have some parameters in the one form that you can study their RG flow, and there was some conjecture. I don't remember, to be honest. There was some conjecture that one of these flows.
I would just because I assume that when you do some RG,
Yes.
you do a one computation and then you renormalize and things. So I thought that might be related to just try to
Understanding the quantum aspects.
Classical.
I see. No, we didn't do in that point one computation. It was that we studied the flow.
Yeah, well, I ask this. Have you or has anybody
With boundaries.
considered it also boundary in sigma? So you start in 4-dimension with the CP1 and sigma, and then you end up analyzing boundary conditions on on the road. But if you put the boundary in sigma, okay, maybe you have to consider some other boundary conditions from the gauge fields.
No,
boundary in sigma, and there is a whole universe of analyzing whether these boundary conditions could be integral or not. Have you any progress in this area?
So I remember you asking this question before and me saying I don't know, and that was me being ignorant about the existence of work addressing that question. Which is the Roland Mittelstone and David Skinner were the ones who did the diamond. The first work they did in this context was precisely analyzing this Chern-4D Chern-Simons theory with boundaries on the two-dimensional map.
Okay, this is just a very silly question about the nomenclature. Why people call it anti-SFQL? I mean, I would expect SFQL or anti-SFQL to be just equivalent.
Yes.
Cases. But why people stick to anti-SFQL?
No, that's me because they are equivalent. You can use SFQL or anti-SFQL. Yes, they are completely equivalent. I don't know why. Probably because the kind of the Bible in this story, which is the book by Woodhouse and Mason, they do anti-SFQL. But for example, Lewis likes SFQL. He always writes SFQL.
I'm also, it's very nice, this diamond picture. So
yes.
If you put it, I can just. I understand that you have to consider examples, so you can start from the top and then the root of path, and then you land in the same theory.
Yes.
But there are some examples in some integral two-dimensional theories that you can obtain from the anti-SFQL ideas. Which I don't know if you can get them from 4-dimensional Chern-Simons, like I don't know, KDB or linear. So is there any hope that it's diamond that is telling you that there are some integral models that so far haven't taken this integration from CP from 4-dimensional Chern-Simons that should be possible to.
Well, so this is similar to a classification question. So yes, I agree. There are many there. So the reason why this was done is because it was known that many 2D integral models could be obtained from dimensional reduction, and so there are many 4-dimensional anti-SFQL Mills models whose origin is not known from 6D Chern-Simons theory in vector space. But again, it's not clear if because no one did it or because you can't. So it fits along the same lines of the question of a general classification of theories, whether these diamonds, the parent theory of 2D integral field theories.
Well, I think one last question is already general. So if you have these three-dimensional integral theories, yes, I think because of this dimensional algebra or this Lax notion. So I guess they are very special theories. How do they avoid this naive intuition that if you have like interactions, finite Gaussian interactions, and then you have Coleman modular theory, then the theories are trivial, and you have additional symmetry. So in which way do we go those theories affect topological form? And how do they avoid this trivialization?
It's a fantastic question, and I think that I don't know, but because I think I should know. I should have an answer to this question because it's a very good question, a very natural question to ask. So I'm going to focus in my 3D theory. So my 3D theory, like the one we wrote down explicitly. So I'm not sure if the definition of integrability I gave for that theory is the existence of this infinite symmetry algebra implies that one has the no-go theorems of Coleman. I'm not sure. And therefore, if that will tell you that you cannot have.
Yeah, I guess that Coleman will do it particularly. I mean, probably those are just for the S matrix, and you have the S matrix, we have a massive part of number short range interactions or something. Maybe that's the way probably. But I mean, otherwise, it's anyway, it's very interesting. So, no, I think that those are basically the questions I have. So, and congratulations again.
Thank you very much.
Luciano?
Okay, thank you very much. Kevin, I know you have to go, so I do this very quick. I'm gonna to stop YouTube Live. Para la gente que no está viendo en YouTube, voy a parar y después vamos a retomar. Once we are live, I'm gonna tell to Diego to read, okay?
Okay.
Okay. Diego, cuando quieras, puedes leer.
Bueno, antes que nada, felicitaciones, Joaquín. O sea, recuerdo decidimos que la tesis está aprobada con mención especial, así que voy a leer el dictamen. La tesis doctoral, Teorías de Chern-Simons e Integrabilidad, aborda diversos temas relevantes dentro del área de la teoría de campos. En particular, explora la correspondencia entre teorías de Chern-Simons y modelos integrables en diferentes números de dimensiones. El formalismo desarrollado y estudiado por el licenciado Liniado ofrece una perspectiva novedosa para el análisis y la clasificación de las bien conocidas teorías integrales en 2 dimensiones. Además, la tesis introduce novedosas generalizaciones de este marco, permitiendo una descripción de teorías integrables en dimensiones superiores. La tesis está bien estructurada y redactada con claridad, presentando los distintos casos con marcada coherencia y progresión lógica. La defensa oral fue igualmente clara y rigurosa, integrando los diversos aspectos de su tesis en una perspectiva unificada. El licenciado Liniado respondió a todas las preguntas del jurado con seguridad y precisión, demostrando un excelente dominio del tema y una profunda comprensión de los problemas abordados. En conjunto, la tesis constituye una contribución valiosa y original al campo de los modelos integrables, tanto en términos de desarrollo conceptual como de innovación metodológica. En base a lo expuesto, este jurado califica la presente tesis como aprobada con mención especial.
Muy bien, Joaquín, ¿algunas palabras finales?
Bueno, muchísimas gracias por venir acá. Thanks, Tim, for being the examiner. Ha sido un placer estos años y este doctorado. Y bueno, espero que así sigan siendo los años vencidos. Muchas gracias.
Well, Thank you very much. Gracias, Joaquín. Tim, any words?
No, just congrats, Joaquin, and yeah, we'll be seeing you soon.
Hopefully, yeah.
Thank you, team. See you.
Bye,
Diego?
thanks.
Diego,
No,
¿unas palabritas finales?
Sí, lo mismo, disfruté un montón. Una anécdota, yo lo conocí a Joaquín, creo que hace como 4 años, cuando estaba empezando a estudiar estas cosas, y entonces nos propuso a mí y a Horacio contarnos lo que estaba estudiando, y en su momento yo pensé, este Joaquín está metiendo en un tema súper difícil. Horacio es un genio, pero no es el campo en el que él trabaja. Yo rápidamente me di cuenta que si bien hice cosas de integrabilidad también estaba fuera de mi liga, pero bueno, rápidamente me di cuenta que tenía la autonomía para, no sé, nunca, ni siquiera se me ocurrió sugerirle, mirá dónde estás saliendo. A la vista están los resultados, así que te felicito. La tesis estuvo muy buena y aprendí un montón leyéndola.
Vale, gracias.
Bueno, muchísimas gracias. Muchísimas gracias, Joaquín, Diego, Tim, que recién avisó que se iba, y Kevin también, que se tuvo que ir. Agradecemos a todos los que estuvieron viendo por YouTube. Doy por finalizado el acto de la defensa de tesis doctoral del licenciado ahora doctor Joaquín Liniado. Y esperamos que pronto haya otra tesis, creo que el 9 de septiembre. Hemos terminado con la sesión de tesis de casi 30 en un mes y piquito con el receso, así que bueno. Quedamos a disposición, Joaquín, como te dije.
Muchísimas gracias por toda la gestión, Luciano. Sé que estuvieron como locos y te agradezco mucho toda la gestión que hiciste.
De nada, Joaquín, para eso estamos para trabajar, porque si no, se nos cae todo. Así que bueno, muchísimas gracias. Cierro el acto. Ahora nos vemos en el aula. Hasta luego, y a todos los que nos están mirando también. Nos vemos.